It all counts. I'm very happy to present our award talks session. First, we will have two winners of the Best Paper Award. The first of those is Space Efficient and Noise Robust Quantum Factoring by Sayon Raghavan and Vinod Vaikuntanathan. And Sayon will be giving the talk.
Can everyone hear me? Excellent. Hi, everyone. I'm Sayon. This is joint work with my advisor, Vinod Vaikuntanathan. And firstly, thanks very much for this award. We're obviously super stoked. And with that, factoring. So this problem of given a large integer that I'm going to denote by big N, breaking it apart into its prime factors has been on the minds of mathematicians at least as far back as Gauss, as you can see. And maybe this isn't surprising, it's kind of a very foundational problem to number theory. And what's more, it gained a lot of concrete importance in the 1970s with the introduction of the RSA crypto system. So in particular, if you could solve this problem, you would completely break this scheme. So it's extremely important to cryptography. And in addition, as we'll see, it's an important application of a future quantum computer. So in terms of what we know about factoring without the assistance of a quantum computer, there's a long line of work, which I don't really have time to get into, but you can check out this survey by Carl Pomerantz. For now, suffice it to say that the best thing we have is sub-exponential time. So it runs in roughly 2 to the n to the 1/3 time, where n is the bit length of the number we're trying to factor. Okay, so the story completely changes if you allow quantum circuits to come into the picture. So Peter Shor in the 90s came out with this algorithm, a really nice algorithm that shows how to factor in quantum polynomial time. So the kind of model you should have in mind is that you pass the integer n to a polynomial time pre-processing procedure that's classical. And then all of this information gets passed along to a quantum circuit, which we're going to run some number of times. And then we stitch the results of all these runs together and feed them to some classical post-processing procedure. And that's when we finally get our factors. And the efficiency metric we're really going to be concerned with is this quantum circuit in the middle. So when I say Shor runs in n squared gates, that's just with respect to this quantum bit in the middle. Okay, and what's more is Shor is also extremely lean in terms of space. So it only basically requires a linear number of qubits. And you might ask, well, why do we care about space so much? And the reason is that quantum qubits are especially prone to decohering and becoming corrupted at any given point in time, even if you're not operating on them. So the more qubits we have, the more likely it is that any one of them is going to just become completely corrupted, even if we're not looking at it. And this is nicely summarized in this quote by Craig Gidney, where he says that memory is really one of the most expensive things you can do. These asymptotics look pretty good. So why improve this? So Gidney and Nikera did kind of a full stack resource estimation of what it would take to break crypto using Shor's algorithm. And they came out with these resource estimates, which are way, way more than what we can currently do in practice with a quantum computer. And you might ask, well, why is this the case when these asymptotics look so good? And there's really 3 reasons I want you to keep in mind. So one is the number of qubits in Shor's algorithm. 2 is the number of gates. It requires quadratically many gates in the input. And thirdly, both of these things get multiplied with the overheads that come from detecting and correcting quantum errors the entire time. And that's why these numbers are so large. So we'd really like, ideally, to be able to make improvements on all 3 of these fronts: space, gates, and error correction. And we didn't really have any major improvements to Shor's algorithm for nearly 30 years, until last year when Oded Regev came out with this really nice quantum algorithm that essentially needs a quantum circuit of size n to the 1.5. And I'll briefly take a moment to step aside for a moment and also say that Shor's algorithm also adapts to discrete log over any group. And there was follow-up work by Akera and Gartner that show how to adapt Regev's speed up to discrete logarithms mod n, but crucially not general groups. That's all I'll say about discrete logarithms for this talk. Okay, so that's the good news. We have a smaller circuit thanks to Regev. The bad news is that Regev's circuit also requires significantly more qubits than Shor's algorithm. It needs n to the 1.5 qubits, and we'll see why. So with that in mind, our first result is a best of both worlds result, where we show that we can re-implement Regev's circuit in a way that asymptotically preserves the gate complexity, but we bring the number of qubits down to match Shor. And I want to mention that not only are these improvements asymptotic, but they actually kick in for 2048 bits, which is what we care about for RSA in practice. So these estimates are a little bit coarse, but we probably get more than an order of magnitude savings than Shaw in terms of, than Regev in terms of the number of qubits. So to state our second result, I need to introduce another variable, which is the number of times you run this quantum circuit in the middle. So in Shaw's algorithm, it suffices to just run his circuit O of 1 times. So in total, you need to run O of n squared gates, more or less, without any errors. So you end up needing a per gate error probability of something like n to the minus 2. And with Regev, although we have a smaller circuit, we also need to run it many more times. It turns out that you need to run the circuit root n times. And so you might ask at this point, well, hang on a second. If we have an n to the 1.5 size circuit and we're running it n to the 0.5 times, that's really an n squared size circuit. What have we gained here? And the point is that the hope is that in practice, the challenge is just manufacturing this quantum circuit. And once you have the circuit running it several times, it's not that big of a deal. So that's why we still view Regev's circuit as an improvement. But the point still stands that Regev's classical post-processing does require every single one of these runs to be free of logical errors. And the next question you might ask is, well, why can't I do something easy, like, say, run it several times and then use a majority vote to filter out the errors? And the reason is that even if this algorithm runs completely correctly, it's very far from deterministic. You're going to get wildly different outputs every time. So you're not going to be able to do something nice like a majority to aggregate these outputs together. So this really is a limitation. So, if what you end up with is you still need to run a total of n to the 1.5 times n to the 0.5, which is n squared gates. And you need to be able to run those without logical error. So you're stuck with the same per gate error probability that we had in Shaw's algorithm. So in this respect, Regev does not improve over Shaw. And there's our second result. So we show that we can modify Regev's classical post-processing procedure to tolerate a small constant failure probability per run of the circuit. And what this means is that the per gate error probability now only needs to be n to the minus 1.5, which is better than both Shaw and Regev. So, and there was also a similar result in a concurrent work by Akera and Gardner. So this is a quick summary of our results. So we improve on the space complexity of Regev to match Shaw, and we improve the noise tolerance with respect to both Shaw's and Regev's algorithms. Okay, so I'll begin with a quick overview of Shaw's and Regev's algorithms, our two protagonists. So the main idea of Shaw's algorithm is finding square roots of 1. So the goal is just to find an integer z that's not congruent to plus or minus 1 mod n, such that when you square it, you do get 1. And the reason this is so nice is that this means n is going to divide z squared minus 1, which factors like so, but it's not going to divide either factor individually. So I can take the GCD of one of these factors with n, and that would give me a non-trivial factor of n. And in fact, pretty much every factoring algorithm we have, quantum or classical, boils down to this task. Okay, so one of Shaw's many insights in his paper is that this can be reduced to a problem called period finding. So I'm going to focus on a particular value of n just for clarity. And so Shaw's algorithm proceeds as follows. So he's going to start by choosing a random square as a base. I'm going to pick 4 in these slides. And he looks at the powers of 4, mod n. And eventually they're going to start wrapping around. And what's more is if you look really far along, they're actually going to start repeating. And what I want to do is I'm going to let R be the period of this sequence, or equivalently the first position where I see a 1. And now the point is that 4 to the R is 2 to the R squared. So 2 to the R is a square root of 1 mod n. And with some luck, it's not going to be plus or minus 1. So this is going to give us our factor. And when I say luck here, I mean with respect to the random choice of the base that I specified as 4 earlier in the slide. Okay, so Shaw's second insight is that quantum computers turn out to be extremely well suited to this period finding task. So roughly how does this algorithm go? So he's going to set up a superposition over many values of z. And z could be as large as big N. It's usually going to be a bit bigger, but we don't care because we only need log z many qubits. And you can kind of keep log z in the back of your mind as a crucial efficiency metric. And then what he does is he computes this function 4 to the z mod n in superposition. And this is going to give us the above picture. And by that, what I mean is that I have the different values of z along the x-axis. And then for each value, I have a stripe. And the color of that stripe corresponds to the value of this function. So what you get is kind of this periodic picture. And we have this on the quantum computer. And what we'd like to do is extract the period of this picture, or equivalently its frequency. And this is exactly what Shaw does. So he can apply a quantum Fourier transform to the Z register and measure. And it turns out that what you get is a noisy multiple of the frequency 1 over R. Then you pass this to some classical post-processing procedure and you can recover the period R. And that's Shaw's algorithm. And I've also bolded the period in red, which is around 910. Okay, so now let's move on to Regev's algorithm. So Regev's main idea is to add dimensions. So what we did before was we exploited the periodicity of this function that takes a single index as input and maps it to 4 to the Z mod 3763. Now let's make life a little more complicated for ourselves. We're going to take in two indices, Z1 and Z2 as input, and map them to the product of 4 to the Z1 times 9 to the Z2 mod n. And why does this help us? So let me explain this picture over here. So on the x-axis, I have the exponent Z1. On the y-axis, I have the exponent Z2. And again, it's the same story. A different color for a pixel corresponds to a different value of this function. So now what we have is this kind of 2D periodic picture, and we'd like to be able to find a period, basically. And the main insight is that because we've lifted the number of dimensions up, there are now many 2D periods. And what's more, these periods are much closer to the origin than in Shaw's algorithm. And I've marked them in red. So, in Shaw, the period was something like 900. Here, they're more than an order of magnitude smaller. And this is where we're kind of going to get our savings. And once you have this insight, actually constructing the quantum circuit follows much the same blueprint as Shaw. So why does Regev get a speed up? So what I've pictured here is when the dimension d is equal to 2, but you could also play the same game in more dimensions. And the size of the periods, it turns out, in general, is something like 2 to the n over d. And the main task in Regev's circuit is to compute a product of d powers, where each exponent is at most 2 to the n over d. And the point is that, let's say we compute this with something like repeated squaring. Even just to compute one of these powers, we're going to need at least n over d multiplications. And the magical observation by Regev is that if you cleverly do your arithmetic, this is actually enough, even though you have more powers to multiply together. And he's crucially using the fact that these bases are small, but I don't have time to get into that. So once you have this, you get a factor of d speed up, because we only need n over d multiplications, Shaw needs n, so out comes a factor of d. So wait a second, if increasing the dimension allows us to save a factor of d, why not just blow it all the way up to n? This would give us a near linear sized quantum circuit for factoring. And the reason is that it turns out that the classical post-processing needs to solve a d-dimensional lattice problem with approximation factor roughly 2 to the n over d. So this is going to get much harder as d grows. And so the sweet spot is d equals root n, because in that case, we hit the LLL regime. And this is exactly what Regev does. So that's how we get a factor of d savings, which for us is root n, and that's how he gets his n to the 1.5 size circuit. So now let me talk about our first result, which is improving space complexity. So to do that, I first need to tell you why Regev needs all these extra qubits. And as I mentioned earlier, the main issue is computing this product of powers. And the problem really is that repeated squaring mod n is not something that you can do in place on a quantum computer. And as Gandalf understands well, this is a distinctly quantum problem. The issue is that squaring mod n is not a reversible function. For example, it maps -1 and 1 to the same output. And classically, this is not a problem. I could put my input in one register, square it, write the result in another register, and erase the contents of the first register, and I might as well have squared in place. The issue is that quantumly, we're not allowed to carry out this operation where we erase the contents of a register. We really need quantum circuits to be reversible, and this is a constraint that comes all the way down from quantum mechanics, so we don't expect to get around it. So what Regev needs to do instead is square out of place. And what ends up happening is that you kind of get this bloated intermediate state because of how many squarings you have to carry out. So each squaring adds n qubits, and we have about n over d squarings to make. So in a total, you have n squared over d qubits. And since d is root n, that comes out to be n to the 1.5 qubits. So now let me pause for a second and take an aside. So Shaw is basically Regev's algorithm for d equals 1. So shouldn't this mean that Shaw also requires, in fact, a quadratic number of qubits? And it turns out no. And the reason is that Shaw is not doing repeated squaring on the quantum computer. Instead, what he does is he pre-computes a to the 1, a squared, a to the 4, a to the 8, and so on classically. And then quantumly, the only thing he does is he multiplies the right subset of these together. And the hope here is that unlike squaring, multiplication is reversible, which you might believe, but it's actually not entirely obvious. I'll say a bit more about that later. And so now the obvious question is, why doesn't the same pre-computation trick work for Regev? And let's count how many bits we'd have to pre-compute. So there are d bases for us to worry about. There are n over d powers, since our exponents could be as large as 2 to the n over d. And each of our outputs is an integer mod big N, which is going to take n bits to represent. So that's a total of n squared bits. So if our circuit's going to look at all these bits, it better have at least n squared gates. And now we've lost our hope of obtaining a speed up over Shaw. And yeah, exactly. So we're going to get around this problem using 3 main ideas. So the first one is what we call Fibonacci exponentiation. And the point is that if you have one accumulator, you're kind of boxed into doing something like repeated squaring, which we saw is not going to cut it on a quantum computer. So what if I gave you 2 accumulators instead? And the point is that now I have the ability to carry out this operation where I take one register and I multiply it into the other. And there's a nice observation by Kaliski in 2017 that you can actually use this operation as a primitive for exponentiation. So if I take 2 registers and I say start with A in both registers, I can kind of play a game of leapfrog between the 2 registers where I multiply the left into the right, then the right into the left, and go back and forth. And you end up with this sequence of powers. And what you'll notice is that the Fibonacci numbers start appearing in the exponent. So contrast this with repeated squaring, where the easy thing to compute is a to the 2 to the k. Here it's a to the kth Fibonacci number. Now, the second thing we have to deal with is how do we actually implement this multiplication operation? And the issue is that, as I mentioned earlier, we care a lot about reversibility, but this isn't reversible if a and n share a common factor. For example, if n were 6 and a were 2, there would be a collision like so. And our idea is basically to get, and I'll mention quickly that this isn't something that Kaliski had to worry about because he was considering classical reversible computing, which is a slightly different setting. But this is something we have to think about on a quantum computer. So our solution based on ideas by Shaw is to basically certify that a and n are relatively prime by explicitly providing the inverse of a mod n in another register. So instead of implementing this multiplication that we'd ideally like to implement, we have to implement this slightly bigger gadget where we take a together with its inverse and b together with its inverse as input, and then map it to a together with its inverse and ab together with its inverse. And once you have this idea, it turns out that this operation is not too hard to implement, even with an out-of-place multiplication circuit. So that's how we get around that problem. And finally, if we want to compute a power, and we want to use this Fibonacci exponentiation technique, we'd better be able to decompose the exponent as a sum of Fibonacci numbers. And in repeated squaring, we don't have this problem because our inputs are in binary. It's already written as a sum of powers of 2 for us. Here, we're not so lucky. But thankfully, this is doable with a straightforward greedy algorithm. You just subtract off the largest Fibonacci number that fits and kind of rinse and repeat. And it turns out that if you work it out, these are the costs of that greedy procedure. And crucially, they don't hurt any of our asymptotics, so they don't become bottlenecks. OK, so once you put those 3 things together, you get our improvement. And so here are some concrete comparisons between Regev's original circuit and our one. So the number of multiplications is some constant factor more, primarily because we have to work with these inverses the entire time. But on the other hand, in terms of space, we're much leaner. OK, and the main idea, I'll just reiterate, is that squaring mod n cannot be implemented in place, but we could hope for multiplication to be implemented in place. And so we can exponentiate with 2 registers using this exponentiation technique. And crucially, we're not going to need to pay with extra registers as we go along. So with that, I'll talk about our second result, which is improving noise tolerance. So to tell you about Regev's post-processing, I first have to tell you what comes out of his circuit. So to do that, I'm going to define these 2 lattices. So L is going to be the collection of vectors Z such that this product of exponents maps to 1 mod n. And I'm going to let L star be its dual lattice. And it turns out that what comes out of Regev's circuit is a random vector from L star plus some exponentially small L2 noise. And I want to quickly mention that if you've seen Shaw's or Simon's algorithms, it shouldn't be too surprising that the dual lattice comes into play here. It's much the same story in either of those algorithms. OK, so then what does Regev's classical post-processing do? So let me explain this diagram. So I've just visualized the 2D case here. And the black points are my dual lattice L star. And these gray balls around them are the exponentially small L2 balls. So what Regev does is, given O of D samples that come from these gray balls, post-process them somehow to roughly recover a basis for the original lattice. That's what Regev's algorithm does. But now if we have actual quantum errors in some of our runs, the issue is that we're going to have some what we call Hamming errors, which are basically uniformly distributed over 0, 1 to the d. And in particular, they have nothing to do with the lattice. They're almost certainly not going to fall in the inside the gray balls. And of course, we're given these samples in one giant bundle. We don't know which is which, so we'd like to somehow disentangle them. And that's exactly what we do. We show that we can detect and filter out these Hamming errors. And then once we're down to just L2 errors, we can feed those along to regev's post-processing procedure. Okay, so how do we do this? So the main idea, which was suggested to us by regev, is that the samples that only have L2 errors are going to share these linear relations. So you can see that I've circled in purple 4 points that form a parallelogram in the lattice. And this can be written out as a linear relation. And now what's more is I have a sample. I have a noisy sample that's close to each of these lattice points. So I could write the same equation out using these samples instead. And now instead what I get is an approximate linear relation. So now the idea is that these samples are going to share approximate linear relations. And what's more, we can show that with high probability, there is no such linear relation that uses even one of the Hamming errors, the red x's. So we're basically going to search for these relations and use them as a certificate that a certain point in our set of samples is only an L2 error. So our second idea is to kind of formulate this as a lattice problem. So if we're given vectors v1 to vm and 0, 1 to the d, and we stack them horizontally into a matrix, it turns out that this task is really about finding a short vector b, such that if I multiply this matrix on the right with b and reduce it mod 1, I get a short vector. And this is really an approximate SIS problem. And in particular, that means we can solve it with exponential approximation error using LLL, and that's really all we need. And now that I've told you that, I can actually state our full algorithm. So we do this to find some short solution B. And then with high probability for any index in the support of B, the corresponding sample is only an L2 error. It's not a Hamming error. So it's going to be close to the dual lattice. We rinse and repeat this until we have enough samples. And then we're just going to feed them along to regev's post-processing procedure. So that's it. That's our algorithm. And now let me just kind of provide some concrete results and summarize. So regev's original algorithm needs to make about 6 root n multiplications per run if you work out the parameters, and they have root n runs, and they don't need, and he can't have logical error in even a single run, which means that his error per multiplication needs to be something like 1 over 6n. And now with our procedure, there's some freedom in how you pick the parameters. This is just one choice, but we have about twice as many multiplications per run, but then we have about 10 times as many runs. But we only need the logical probability to be about 10% per run. So if you work it out, you get this asymptotic where we just need to be able to multiply with error probability 1 over root n, which is asymptotically better than regev's and also thinking back Shor's algorithm. And what's more, this is actually a concrete improvement as well. The crossover point is something like n equals 500, which is well within what we need for an improvement in practice. So with that, and the main idea is that these good samples are going to share linear relations that we can search for using LLL, and using that, we kind of filter out the Hamming errors. So with that, let me quickly finish with some open questions. So firstly, why enter the 1.5 gates? So there's really 2 questions hidden here. So the first one is, if I insist on using polynomial time classical post-processing, this really seems like an artifact of regev's specific algorithm. At least in my view, there's no reason why some completely different idea couldn't give a faster circuit. And there's a second question you can ask, which is, well, okay, we can scale classical computation very easily. So what if I allowed you to make the classical post-processing super polynomial time? In particular, anything faster than 2 to the n to the 1/3 is still better than what we know how to do without the assistance of a quantum computer. And in this setting, it turns out that, in regev's algorithm as is, you can just blow up the dimension and you would get a circuit of size something like n to the 4/3. But can we do even better than that? And finally, maybe the elephant in the room question, does regev's algorithm and its follow-ups actually bring us closer to breaking RSA 2048 using a quantum computer? And at least my answer would be that it might with further optimizations, but not yet. And the reason for this is that there's a long line of nice constant and polylog factor optimizations to Shor that, as far as we know, don't seem applicable to regev, but they make Shor extremely effective for small problem sizes. And with that, I'll close. Thanks very much.
Thank you. If anybody has a question, please come up to the microphone. It's a Zoom thing.
So, I mean, just to understand the conclusion on the slide, I mean, you quoted an article earlier that I think said 20 million gates as an estimate for breaking RSA 2048. You're saying that your algorithm doesn't lower that number concretely?
We don't know yet, because someone needs to go ahead and do a full stack resource estimation for Regev.
All right. Let's thank Sion again. Congratulations. Our next talk is also a Best Paper Award winner. It is STIR, Reed Solomon Proximity Testing with Fewer Queries by Gal Agnon, Alessandro Chiesa, Giacomo Fenzi, and Elon Yogev, and Gal is going to be giving the talk.
Oh, thanks. Thanks, Leo, and thanks, everyone. So yeah, this is joint work with my amazing co-authors, Sandro Chiesa, Giacomo Fenzi, and Elon Yogev. Okay. So, not going forward. Okay. So the overarching goal of this work is to construct succinct non-interactive arguments of knowledge, or SNARKs. So in a SNARK, we have a prover claiming to know a witness to some NP statement X, and a verifier wants to be convinced of this. So the prover could just send the witness, but what we want is something that's much, much shorter than that. So we want a prover to send a single message, and for this to be much, much shorter than the witness size. And specifically in this work, we're going to be interested in the pure random oracle model. So both of the parties are given access to a random oracle, and there's no other cryptography involved. So these SNARKs are used in practice. So practically speaking, you take the random oracle and you instantiate it with a concrete hash function. And these give really amazing SNARKs. They have transparent setup, meaning that all everyone needs to know is just which hash function we're using. They're highly efficient. There's no public key crypto, nothing complicated going on. And they're plausibly post-quantum secure, by which I mean that they're secure in the quantum oracle model. So if you believe that your hash function is quantum secure, your SNARK is going to be quantum secure as well. And these are used in practice to secure billions of dollars in real-world transactions on blockchains. And there's a lot of companies that either work on constructing SNARKs or have SNARKs as part of their product in some way. So how are SNARKs in the random oracle model constructed? Well, the main way to do this is using interactive oracle proofs, or IOPs. So an IOP, you can think of it as an interactive analog of a PCP. So you have a prover and a verifier, and they interact over multiple rounds. And after the interaction, the verifier queries the prover's messages at a few locations and decides whether to accept or reject based on that. And the parameters that we're going to care about for IOPs are the proof length, so the number of symbols sent by the prover, and the number of queries sent, read by the verifier from the prover's messages. So we take this IOP, and then we compile it with something called the BCS transformation into SNARK in the random oracle model. And remember, we wanted to have a very succinct proof. So what is the argument size of this? If we want lambda bits of security, we get argument size lambda times q times log L. And this tells us that if we want a really, really short SNARK, then we should construct an IOP with small proof length, but even more crucially, very small query complexity. And OK, so these IOPs, the way they tend to be constructed is we have some very efficient protocol going on at the beginning. And then after that, we have a Reed-Solomon proximity test. And this tends to be the real bottleneck in these protocols with regards to query complexity. So in the rest of this talk, we're going to be trying to construct better Reed-Solomon proximity tests. So what is a Reed-Solomon proximity test? Well, first of all, I need to define Reed-Solomon codes. So I'm defining Reed-Solomon codes with the notation n, d, and rho. So we have some finite field, and we take degree d polynomials and evaluate them over a domain of size n. And the rate rho is the degree over the size of the domain, so it's the inverse of the amount of redundancy in the code. For technical reasons, we're always going to be thinking of n and d as powers of 2, and the evaluation domain, I'm not going to specify it specifically in this talk, but it's a multiplicative subgroup of the field. These are not going to be very important in the talk, but we need them for technical reasons. Okay, so what is a IOP of proximity for this code? We have a prover and a verifier and a function f in the sky. And the prover claims that this function is a code word, as a Reed-Solomon code word. They interact over multiple rounds, just like in an IOP. And after this, the verifier reads a few locations, both from f and from the communication sent by the prover, and decides whether it's convinced that this f is actually a code word. So we want that if f is really a code word, then the verifier should always accept. And if f is far in Hamming weight from any code word, then the verifier should accept with probability at most 2 to the minus lambda for a security parameter lambda. And here I mean a notion called, this notion is round by round soundness. So it's a stronger notion than standard soundness, which is what you actually need for the BCS transformation. And what we want is to have this kind of protocol while minimizing the verifier queries both to the function f and to the subsequent prover messages. So now I can state our results. We construct stir, which is a new IOPP for Reed-Solomon codes. The round complexity is log d. The proof length is linear in the original code word. And crucially, the query complexity is lambda, our security parameter, times log of log d over minus log square root of rho plus log d. This is a very complicated expression. This is for code words that are of distance 1 minus square root of rho. So how should you parse this complicated thing? We should think of lambda as being the largest thing here. So it's much larger than log d. You should think of the rate rho as being something, some constant like 1/2 or 1/4. So basically this expression is lambda times log d. The previous best known protocol was the Fry protocol, which has roughly lambda times log d. So this multiplicative factor of the security parameter has improved exponentially in stir. And so you're going to see this square root of rho a lot of times in this talk. This very roughly comes from the Johnson bound. And using some list decoding assumption, we can turn that into rho, just the rate. This improves constants. But in order to have everything be with no assumptions in this talk, you're going to just see the square root of rho all the time. Okay, so we wrote an implementation of this in Rust based on the ArcWorks backend, which is a backend for constructing, it's a library for constructing these kinds of snarks and things like that. We implemented both Fry and stir with a lot of optimizations, and we compared the two. So in comparison to Fry, the fact that we have fewer queries leads to concretely a smaller argument size and smaller verifier hash complexity across all parameters. And this hash complexity is really important because these snarks tend to be used in a recursive manner, meaning that you later you have some proof and you take the verifier and then you prove something about the verifier itself. So the more complicated the verifier, the larger the proof is for the recursive and the recursive proof. So the fact that we have smaller hash complexity means this is much more recursion friendly. The prover time is roughly the same in both Fry and stir, where the bottleneck is really just evaluating the initial function. And there are bigger improvements when the degree and the rate increase. So let's look at a few numbers. So in everything here, we're trying to get 128 bits of security. There's a few optimizations that I'm not going to get into. But so for degree 2 to the 24 and rate 1/4, Fry has roughly 180 kilobytes size, and stir is roughly 110. So it's better than 1.5 times smaller. The hash complexity of Fry is 3.5K, with stir is 1.8K. So it's even better. And this becomes even more drastic when we go up to the rate and the degree. So for degree 2 to the 30 and rate 1/2, Fry has a roughly 500 kilobytes, whereas stir is less than half of that, at 200. And the hash complexity tells a similar story, 10K versus 3.8K. And let's look at some graphs. Well, here, fry is in red and stir is in blue. So you can see that the argument size and verifier hash complexity is much higher in fry versus stir. The prover time is roughly the same in both cases. And the verifier time, so the verifier in stir does a little bit more arithmetic work than in fry. So for small degrees, the fry verifier is a bit faster, but for high degrees, the stir verifier becomes significantly faster than fry. So let's see some techniques of how we get this. So in order to understand our protocol, we have to review something called a Reed-Solomon code folding. So we start off with a Reed-Solomon code with evaluation domain size n and degree d, and we want to simplify it. We want to we have some folding parameter k, which you should think of some constant like 16, and we want to simplify the code to have evaluation domain n over k and degree d over k. So how does this look? We have a function f, and it's over a domain of size n, and the verifier chooses a random some random field element alpha. This defines the folding of f at alpha, which is over domain of size n over k. And you should be thinking of this as roughly the following. So for k equals 2, the folding of f at alpha is you take the even coefficients of f, you take the odd coefficients of f, and you take a linear combination of them based on alpha. And this can be generalized to all k's that are powers of 2. And that's how this actually looks. So this is local in the sense that if we have access to f and we want to compute the folding of f at alpha at some point, we can query f at k locations, do some computation, and then we can figure out what the folding is. So this is the virtual function. And crucially, this is distance preserving. So if f is 1 minus square root of rho far from a Reed-Solomon code word, then with high probability, the folding of f is also going to be far from Reed-Solomon code word, but with the factor of k. So if crucially here, this is rate preserving. So remember, the rate is the degree over the size of the evaluation domain. So that's d over k over n over k. So it's again d over n, which is the original rate we had. So now that we know how to simplify the code somewhat, this gives us a path to testing the code. And this is what fry is going to do. So we have the function f. We're going to fold it at a random location, just like before. And now we could think of trying to fold over and over and over and over again to simplify it over all the time. But then if we need to, at some point, we're going to need to actually query this function. And this is going to blow up the query complexity. So we're not going to do that. We're going to have to stop the recursion in some way. We're going to do that by asking the prover to send a function f prime. And this is meant to be the same polynomial as the folding of f at alpha. So of course, we don't trust the prover to send something, to send anything. So we're going to have to check that it actually sent the right polynomial. We're going to do that by simply comparing the two at t random locations. Just check that the folding of f and f prime are equal. And then and f prime is supposed to be a polynomial. So we want to actually test that. So we're going to recurse on f prime. OK, so in the actual fry protocol, there's going to be some consistency check between, the consistency checks between iterations are correlated, but I'm not going to get into that in this talk, in this high-level overview of fry. So let's see why this works. So suppose the recursion was fine. So f prime is actually a Reed-Solomon code word with degree d over k and evaluation domain n over k. So since f is far from Reed-Solomon code word, the folding is going to be far from any Reed-Solomon code word. F prime is such a code word, therefore f prime and the folding of f disagree on at least square root of rho locations. And therefore, the verifier accepts with probability at most square root of rho to the t, the number of queries that we did. So now if we want lambda bits of security, we want the error 2 to the minus lambda, we better set t to be equal to lambda over minus log square root of row queries per round. And this is for every round, we have logarithmic number of rounds because we simplify the function by a constant every time. And so this is why fry has this lambda times log d factor. Okay, so this has been fry. What about stir? The stir stands for shift to improve rate. And the high level idea is that smaller rates are easier to test. So smaller rate means there's more redundancy. And this is going to be easier to test than something with the same rate. So we start off in the same structure. We just take f, we fold it. But now we ask the prover to send a function g, which is, again, claimed to be the same polynomial as the folding of f, but it's going to be much larger. So we're thinking of f as being over evaluation domain of size n. The folding is n over k, and k we're thinking of as larger than 2, so think 16. Then g is going to be over a domain of size n over 2, so it's much, much larger than the folding of f. So now we can't really do this consistency check that we did before because these functions are defined over completely different domains, or G is a much larger domain. So we're going to have some new consistency check, which we call domain shifting. It's a t-query consistency check between the folding of F and G. And at the end of this domain shifting, this defines a virtual function f prime, such that if the folding of f is far from a Reed-Solomon code word, then accept with probability square root of rho to the t, f prime is far from a Reed-Solomon code word, but what code word? Well, it has degree d over k, just like the folding of f, but the evaluation domain is n over 2. So now the rate is much smaller. It's 2 over k times the original rate. So remember, we're thinking of k as 16, so it's like 1/8 of the original rate. And this means that this distance, which is related to the new rate, rho prime, is larger than the previous rate. So now we recurse just like before. And what happens is that we get a sequence of rates where in the ith iteration, the rate rho I is 2 over k to the I times the original rate. So if we want round soundness 2 to the minus lambda, we should set the number of queries in round I to be ti to be lambda over minus log square root of rho I. And because rho I becomes smaller every round, this leads to fewer queries in each round. Now, this expression is a bit hard to parse. So here's a numerical example. So for folding parameter k equals 16, and if we want 100 bits of security, let's say we start off with rate 1/2. So if we're rate 1/2, in order to get 100 bits of security, we're going to need 200 queries. But then in the next iteration, our rate is 1 over 16, so we only need 50 queries in order to get the same security. And in the next iteration, our rate is 1 over 128, so we only need 29 queries, and this keeps going. And so it goes down and down, down. In the previous solutions, so just be 200 in every round. And this is why stir gets such a small query complexity. So what is this domain shifting? What is this new consistency check? So we have the function folding of f at alpha, and we have g, and they're claimed to be evaluations of the same polynomial, but they're over different domains, which is why we call this domain shifting. And the goal is to define some function f prime, derive some function f prime from g, where if the folding is far from a Reed-Solomon code word, then f prime will be far from Reed-Solomon code word with high probability. So let's start with a temporary simplifying assumption that there's only one polynomial that's 1 minus square root of rho close to g. And I've colored the locations in which this polynomial agrees with g with green here. Okay, so because the folding of f is far from any Reed-Solomon code word, so any evaluation of a polynomial, it's also far from p. So there's only a few locations that are where the polynomial p agrees with the folding of f. So I've colored those with green as well. So what are we going to do? We're going to query a random location in the folding. let's call that location Z and say that Y is the value written inside this location. And then we're going to define f prime of x to be equal to g of x minus y over x minus z. And we call this the quotient of g at point z comma y. And why are we interested in this, this weird expression? Well, f prime is going to be far from a Reed-Solomon code word if and only if this polynomial p at z is not equal to y. So this tells us that as long as we don't hit a green location with our choice of z, the function f prime is going to be really far from Reed-Solomon code word. Now, technically, this code word is going to be far from degree d over k minus 1 and not d over k. We have to do some other tricks to correct the degree for technical reasons. And so as long as we don't hit these green locations, which happens with probability square root of rho, because the distance is at least 1 minus square root of rho, f prime is going to be really far from a code word, and then we can recurse on that. And this can be amplified to square root of rho to the t for t queries. Okay, so we have this temporary assumption, but what about removing it? So there might be many polynomials that are close to g. The picture might look like this. So I've colored different polynomials in different colors. And then the problem is that the polynomials that are close to g could potentially cover all of the folding of f. The picture might look like this. So every single location in the folding of f has some polynomial in g that agrees with it. And then the claim that we had before just wouldn't hold because this yellow polynomial agrees with the folding at location z. So in order to solve this, we have to have a new subprotocol called out-of-domain sampling, which at a very, very high level, it forces the prover to choose a unique polynomial and forces the picture to be back to where we started, to have only this one green polynomial instead of all the polynomials. Okay, so now you can sort of understand roughly how the protocol looks. We start with f, we fold it, we have these domain shift queries, we do out-of-domain sampling, and then we recurse on that, keep going all the way down until we get to some constant, which is trivial to test. So I'll conclude. So we constructed stir, a new IOPP for Reed-Solomon codes with very small query complexity. Things that we haven't seen in this talk are this efficient degree correction technique. So remember, previously I said that there was some loss in the degree at some point, and we had to fix that. There's a new technique to do that. Also, we have a concretely efficient high soundness compiler for polynomial IOPs. So one of the ways that we construct IOPs is use a polynomial IOP, which is like a simpler version of an IOP, and then take Reed-Solomon IOPP like stir and put them together in order to construct an IOP, like a proper IOP. And I'll just leave you with one sort of related open problem, which is I'm on the postdoc market. So if anyone's interested, you can take a look at my website. You can talk to me, send me an email, whatever. Thank you.
Time for a couple of questions, if anybody has one.
Thanks for the great talk. I wonder, like, is it hard or easy to extend to binary extension field, or like, if it's hard, what's the obstacle for extend this technique to binary extension?
So extending, yeah. So there have been a few works in the past extending Fry and other protocols to binary extension fields. It seems hard to extend stir to a binary extension field because of this this quotienting that we do. It's very algebraic. It really abuses a lot of the structure. So we haven't really looked into it. I think it would be difficult, but maybe there are other ways to get around it.
Any more? All right. Thank you, Gala, and congratulations again. Our next talk is for a paper that won the Best Paper Authored by Early Career Researchers Award. Used to be a long time ago, we had a Best Student Paper Award, and then we extended a little bit to early career researchers. The paper is Leaky Cryptography from Code-Based Assumptions by Kwang Dao and Ayush Jain, and Kwang will be giving the talk. Congratulations, Kwang.
Okay, let me give a quick test. All right, cool, awesome. Okay, I'll go back. Thanks. So this is joint work with my wonderful advisor, Ayush Jain. And in this work, let me first begin by giving the broader context of our work, which is we are trying to advance the field of post-quantum cryptography. Right now, we're living in a very exciting transition time. NIST has just standardized the post-quantum encryption and signature schemes, and they're getting industry adoptions. However, there's still a lot of work to be done, especially for advanced cryptographic primitives. We want to find new and more efficient constructions for many of these primitives in the post-quantum setting, and also for some primitives, we just want to have new feasibility results. The problem here is that for many of these advanced primitives, and especially in a post-quantum setting, we only know of one way to construct them using lattices. And this is the problem that in our work we try to address. So let me illustrate this problem more clearly by giving you a broad look of the post-quantum landscape, and namely look at the four main branches of post-quantum assumptions and what we know what primitives we know how to build from them. So we have hard problems based on either lattices, codes, multivariate polynomials, or isogenies. By the virtue of being cryptographic assumptions, they all imply one-way functions. However, when we move to public key encryptions, the situation is a lot more mixed. In particular, we have many proposals for either multivariate or isogeny-based schemes that have been broken over the years, especially with the most high-profile break recent being SIDH. In contrast with lattices and codes, we have reasonable confidence that we have secure PKE schemes that are either the NIST winners or the NIST runner-ups. But after we go up from public key encryptions to something more advanced, like identity-based encryptions, then already we only know of one solid construction based on lattice assumptions. There is a code-based construction, but that one is only quasi-polynomially secure, meaning that it is not a very good construction at all. And even more, if we want to go into like advanced proof systems, say in the plane model, like batch arguments, or we want to construct advanced encryption scheme like attribute-based encryptions or fully homomorphic encryptions, then lattices are really the only game in town. We don't know of any other proposals for many of these advanced primitives from other assumptions. And finally, there are primitives like program obfuscation that we just don't know how to achieve right now from post-quantum assumptions. This work is mostly concerned with this part of the landscape here, the part where we have constructions from lattices, but from no other assumptions. Now, you may think that it's fine to have just one construction based on lattices, right? After all, lattices have had a very long history of study. We know its worst case hardness pretty well, and it has survived decades of cryptanalysis. However, I would argue that as cryptographers, we should always be looking out for the next cryptanalysis breakthroughs. This was the case 30 years ago when Shor's algorithm was first introduced and caused this whole progression to post-quantum cryptography. And more recently, there has been continuous attempts to break lattice assumptions with a very, I guess, high-profile preprint that appeared just a few months ago. And I'm sure that many more attacks will come in the future. Secondly, I would argue that if you want to achieve, say, either new feasibility results or improve practical performance of certain schemes, then it is good to look at different assumptions, which may give you different algebraic structures to work with and to leverage. And finally, I feel like we should try to understand all of these assumptions very well because they come from deep connections with other areas in theoretical science and mathematics. So the focus of this work is on improving code-based cryptography. Similar to lattice-based cryptographies, you can sort of see these two classes of assumptions as roughly noisy linear algebra problems. It states that solving linear algebra is easy, but if you add some noise to it, then recovering the secret S here from the noisy sample is hard. Well, that's just a rough outline. But if you look into the details, you'll see that there is a vast difference between the code-based and the lattice-based setting. And it all comes down to the noise model. The noise model in the code-based setting is that the noise vector is sparse, meaning it has many zeros. Most of its entries are zero. Versus in the lattice-based setting, the noises have small entries. And this similarly small difference actually leads to a vast difference in terms of both understanding of worst-case hardness for code-based assumptions, and also a huge gap in what we know to build from code-based assumptions. And so this brings us to the central question of our work, which is that can we try to build more advanced primitive from code-based assumptions? We answer this question by proposing a new assumption. We call this assumption dense sparse LPN. This is a variant of the classic learning parity with noise assumption, but instead of a uniformly random public matrix, we have a more structured matrix distribution, which I'll describe in a moment. And we showed that with our initial cryptanalysis, it seems to be resistant to all the attacks so far. And we conjecture that it also satisfies sub-exponential security. We leverage our new assumptions to build lossy trapdoor functions. This is a simple to state primitive with lots of applications to other areas of cryptography, such as Chauffin ciphertext secure encryptions. And more importantly, in the post-quantum setting, this has only been achieved before by lattices. And this was in the original paper that proposed LTDF 16 years ago by Brent Waters and Chris Pikert. Okay, and one question you might ask is that why are we proposing a new assumption here? Isn't it better to work with well-studied assumptions such as LPN? Well, I hope to convince you that working with LPN has some inherent sort of disadvantage in the noise management that we managed to overcome with our new assumptions. And at the same time, we also needed our new assumptions to circumvent a new attack that we also introduced in this paper against a variant of LPN called sparse LPN. I'll also introduce that in a moment in the relevant parameter regime that we consider in this work. So just to recap here, after our work, we now have a construction of LTDF from code-based assumptions. I also want to mention that there is a isogeny-based proposal based on group actions, but this one achieves very little lossiness, namely a constant number of bits of lossiness, and which is not sufficient for many applications. So for the rest of the talk, I will first introduce lossy trapdoor functions and these noisy learning problems in more details, and then I'll show that natural approaches towards building LTDF will fail for both LPN and also sparse LPN. Then I'll introduce our new assumptions, dense sparse LPN, and then I'll end with cryptanalysis and lots of open questions. Okay, so lossy trapdoor functions. It's a keyed functions where the evaluation key can be set in two indistinguishable modes. You can either set it in injective mode, in which case the function is injective and can be inverted by a trapdoor that's also generated along with the evaluation key. Whereas in the lossy mode, the function has a much smaller range and hence loses information on its input. Lossy trapdoor functions have found lots of applications throughout the years, such as CCA secure encryptions, deterministic encryptions, so on and so forth. So let me also want to go into the differences between LWE and LPN in more details. So these are both noisy learning problems, which I write in this matrix form like this. And the differences here is that in the lattice space setting, we work over the integers modulo q, where q can be polynomially large in terms of the dimension n, or even up to exponentially large. The noise will be low magnitude, meaning they can be discrete Gaussian with some small standard deviations. And so the entries of the error matrix are small. Versus LPN, where we usually work over a finite field or even just a binary field. And the noise model is the Bernoulli noise, meaning that the noise vector will be sparse and have mostly 0 entries. But the other entries can be arbitrarily large in the case of general finite fields. And so the main difference here is that we just have much less room to work with noise in the code-based setting. The noise here can go only up to the dimension, whereas in the lattice-based setting, you can just try to scale it up to the modulus, which can be polynomially larger than the dimension, or even more. So given these noisy learning problems, here's the template that was introduced in the same paper that constructed LTDF. The template is as follows. Okay. So in the lossy mode, the evaluation key is just the LWE or LPN samples. So you have A and then B, which is the sample SA plus E. In the injective mode, it's almost exactly the same, except that you also embed in the special matrix C, which is sort of a suitable code for which you can perform inversion. The function itself, it will take in input from the support of the error distribution. So whichever vectors that have low norm in the norm that we consider, and then mapped it to some image. In particular, evaluation just multiply that small norm vector with the evaluation key from the right. So we have AX and B times X. And intuitively speaking, this achieves lossiness because in the lossy mode here, the second argument is a function of the first argument plus some noise. And this means that if you have this hash function x to a times x be sufficiently compressing, and the noise here is not too much, then we achieve an overall lossiness factor. Inversion, you try to recover a noisy instance of C times X, and then you use the special property of the code seed in order to decode. So I'm not going too much into the inversion one. I will focus on the lossiness argument, which is the main reason why it fails for LPN. The problem with LPN is that we just don't have good ways to achieve compression. In particular, if you look at the argument for when it would achieve compression, you would want the domain, which is a set of T sparse vectors, meaning it has T non-zero entries, to be larger than the range, which is just 2 to the n. And if you work out the parameters, you'll find that the error, the sparsity T is very close to n. It is n over log n. This has an effect on the accumulated noise because you have accumulated a lot of noise in this process. And in order to get injectivity for the other mode, you need the final accumulated noise to be at most a constant, which means that the initial noise must be at most log n over n. And it turns out LPN is insecure in this setting. There's a very simple attack that I might talk a bit more in the cryptanalysis section. Okay. So the point here is we want to achieve compression somehow with better parameters. And we did so by trying to restrict the range of the hash functions by changing the matrix distribution A. We changed this by making the matrix A sparse. We now enter into the sparse LPN assumptions. These assumptions exactly the same as LPN. It's just that the public matrix is a sparse matrix where every column is, say, exactly k non-zero entries and chosen randomly. This is a well-studied variant of LPN with prior cryptographic applications. And when you work with sparse LPN, there's basically two things that you need to remember. The first is that the number of samples that you use cannot be too large. If it's more than n to the k over 2, then you will have sort of two columns that are exactly the same, and that would break the assumption. And secondly, in our work, in order to get compression, we need this sparsity parameter k to be constant or very slightly super constant. And if it's constant, we also need it to have a more structured distribution of the sparse matrix A, which was provided in the work of Applebaum and Catchlon. Okay, so sparse LPN, let's see how the hash function works. So now we achieve our goal, which is that we have restricted the range of the hash function to be the set of vectors that are at most kt sparse. And so if you try to work out this calculation, you'll see that t is now polynomially smaller than n. You can see the example there for a concrete parameter setting. And similarly, this error epsilon is roughly 1 over t, which is now also a inverse polynomial in terms of n. The real question we need to ask now is that, is this parameter regime for sparse LPN secure? And the answer in our work is that it is not. So our tag for sparse LPN is as follows, in the same sort of regime that we can achieve compression. So given the sparse matrix, right, we want to find a dense minor for which you can extract out a sparse vector in the kernel, roughly speaking. So let's go into the details. First, we can pick some random subsets of the rows of A. We'll have some parameters L, which we will tune later on in order to make the attack succeed. And then we will try to find all the columns in A whose non-zero entries are all in the subset S. If there are more than L of them, then there must be a linear dependency. And then we will solve for that linear dependency. And hence we'll have a vector X that is at most L sparse, that is in the right kernel of A. And then we can compute the inner product between the LPN sample and X in order to detect bias. If it was LPN, then it would be more likely to be biased towards 0. So if you do these calculations, then you find that the same parameter for this L is exactly the sparsity parameter needed to achieve compression. And hence, as soon as you get compression for your hash function, you also break sparse LPN. So this is no good. Or, well, could we try to avoid this attack somehow? And the crucial observation that we had is that this attack relies crucially on knowing the sparsity patterns of A. We need to know in each column which of the entries are non-zero or not. If we somehow mask this pattern, then this attack completely goes away. This is the motivation for introducing our new assumptions, dense sparse LPN. Here, we will mask it by multiplying on the left by a random rectangular matrix T. Here, T is rectangular with this constant C being any constant greater than 1. I'll later talk about why we needed C greater than 1. But right now, I just want to say that this idea of trying to hide a code via a linear transformation goes all the way back to Macaulay. And assuming dense sparse LPN in this formulation, then we get our LTDF constructions. And let me also go into the concrete parameters for our LTDF constructions. We have a tunable parameter here, which is the factor of the inputs that we may lose in the lossy modes. And with every factor D like that, we have a corresponding error rate. And you can work out some concrete numbers. So let's say in this setting, if you want to lose like 90% of the input, then error rate is very close to 1 over n, but importantly, it is still an inverse polynomial in terms of n. Okay, and so let me go into the final part of the talk, which is about cryptanalysis, namely that in this error regime, how secure is our assumptions. Okay, so to summarize in cryptanalysis of our assumptions, we basically find three potential attacks. The first one is the generic information decoding set decoding attack, which simply guesses the error coordinates of E, and then if all the error coordinates are 0, then we can find the secrets. This will take time, roughly 2 to the epsilon times n. The second attack, this is inherited from the sparse matrix M, is that the sparse matrix has lots of sparse vector in its right kernel. If we could find such vector by, say, just enumerating all the vectors, then we could also break dense sparse LPN. And this attack will take 2 to the n to the delta, where delta is some constant that depends on the number of parameters. Number of samples. Finally, we have a new attack, which is we try to decompose this dense sparse matrix. And if we could successfully do that, then we could run the attack that I just showed you. But we set the parameters so that this seems to take at least exponential times. And so our conjecture security in this work, which I invite you to break, is that it should be secure against attackers running in sub-exponential time that is the minimum of the first 2 attacks. Okay, so what is this attack that we try to decompose? Well, if we manage to decompose this successfully, then we will break it, right? And this is why we needed to set the constant C to be greater than 1. Because suppose it doesn't happen, then we could try to find the inverse of this masking matrix T. And we do this by just looking for solving some linear equations. We know that the right-hand side is very sparse, and hence lots and lots of equations are going to be 0. Okay, this attack would go away because now if T is rectangular, then you have this residual part T prime, and intuitively you sort of have to guess T prime in order to carry out this attack. Okay, so let me summarize and give you lots of open problems to work with. So in this work, we try to improve our understanding of cryptographic applications from code-based assumptions. To do this, we introduce a new assumptions, dense sparse LPN, and we show one application, which is lossy trapdoor functions. We believe that these assumptions may lead to further advanced primitives down the line, such as, say, private single server private information retrieval, or non-interactive zero knowledge, IBE, ABE, and so on. We also would like to understand this primitive a lot better through cryptanalysis, both with reductions and with determining concrete parameters. If you work on practical cryptanalysis, I would love to talk with you to determine some proposed parameter settings for our assumptions. And finally, our work also points to the need for an improvement in some coding theoretic gadgets that we needed to use in stating our assumptions, and we hoped to somehow get better construction of this gadget. Thank you.
If you have a question, raise your hand, come up, both simultaneously.
Thank you for your nice talk. I just wonder if there's any possibility to build a pre-image sampling function with your lossy trapdoor, just like LWE.
Yeah, so pre-image sampling. We didn't achieve in this work. I will be very happy if you do it. Yeah.
Thank you.
Yeah.
More questions? All right. Thank you, Kwang, and thanks to all the speakers. Congratulations, everyone. Lunch.